Artificial neural networks are one of the central computational tools that enable the modern wave of machine learning and artificial intelligence. When we talk about neural networks in AI, we are referring to parameterized mathematical functions inspired loosely by biological neurons but implemented in a highly abstract and engineering-driven way. The goal of an artificial neural network is to learn a mapping from inputs to outputs by adjusting a large number of numerical parameters based on data. Although the metaphor of biological neurons motivated the early work, modern neural networks should be understood primarily through the lens of optimization, linear algebra, and function approximation. At the most basic level, an artificial neural network is a composition of layers, where each layer transforms a vector into another vector. The simplest unit inside these layers is often called a neuron or a unit. Mathematically, this unit computes a weighted sum of its inputs, adds a bias term, and then applies a nonlinear activation function. If the activation were purely linear, stacking many layers would not increase expressive power because the entire network would collapse into a single linear transformation. The nonlinear activation is therefore essential because it allows the network to represent complex, curved decision boundaries and highly nonlinear functions. To make this concrete, imagine you have an input vector representing some data, perhaps pixel intensities of an image or numerical features describing a transaction. The first layer multiplies this input by a weight matrix and adds a bias vector. The result then passes through a nonlinear function such as a rectified linear unit. This transformed vector becomes the input to the next layer, and the process repeats. Conceptually, each layer is learning a new representation of the data that is more useful for the final task. Early layers often learn simple patterns, while deeper layers capture more abstract structure. The architecture of a neural network refers to how many layers it has, how many units per layer, and how those layers are connected. The simplest and historically earliest architecture is the feed-forward fully connected network, sometimes called a multi-layer perceptron. In this structure, every unit in one layer connects to every unit in the next layer. This dense connectivity gives the network high flexibility but also increases the number of parameters and computational cost. In many modern applications, especially those involving structured data such as images or sequences, more specialized architectures are preferred because they exploit known structure in the data. Training a neural network means finding values of the weights and biases that make the network produce useful outputs. This is framed as an optimization problem. We define a loss function that measures how far the network's predictions are from the desired targets. For example, in classification tasks, cross-entropy loss is commonly used. The network processes training examples, produces predictions, and the loss quantifies the error. The key question is how to adjust millions or even billions of parameters to reduce this loss. The central algorithm that makes neural network training feasible is backpropagation combined with gradient-based optimization. Backpropagation is an efficient way to compute the gradient of the loss with respect to every parameter in the network. It works by applying the chain rule of calculus through the computational graph that represents the network. Conceptually, the network first performs a forward pass to compute predictions and the loss. Then, during the backward pass, it propagates error signals from the output layer back through each layer, computing partial derivatives along the way. Once gradients are available, an optimization algorithm such as stochastic gradient descent updates the parameters. Each parameter is nudged slightly in the direction that reduces the loss. Because datasets are often very large, the gradient is typically estimated using small random subsets of the data called mini-batches. This stochasticity not only reduces computation per step but often helps the optimizer escape poor local minima and improves generalization. One of the defining characteristics of neural networks is their capacity. Capacity refers to how complex a function the network can represent. Increasing the number of layers or the width of layers generally increases capacity. However, higher capacity also increases the risk of overfitting, where the network memorizes the training data rather than learning patterns that generalize to new examples. Managing this trade-off between fitting the training data and generalizing well is a central theme in neural network practice. Regularization techniques are used to control overfitting. Weight decay adds a penalty to the loss that discourages large parameter values. Dropout randomly disables a fraction of units during training, forcing the network to develop redundant, robust representations. Data augmentation artificially expands the training set by applying transformations such as rotations or noise. Early stopping monitors validation performance and halts training before overfitting becomes severe. Modern large networks often rely on a combination of these techniques. Initialization of network parameters is more important than it might first appear. Poor initialization can lead to vanishing or exploding activations and gradients, making training unstable or extremely slow. Modern initialization schemes are designed to keep the variance of activations roughly constant across layers at the start of training. This helps ensure that signals propagate effectively through deep networks. Activation functions also play a major role in training dynamics. Historically, sigmoid and tanh functions were common, but they suffer from saturation regions where gradients become very small. The introduction of rectified linear units dramatically improved the trainability of deep networks by maintaining stronger gradients in many regions of the input space. More recently, smoother variants such as GELU have become common in large-scale models. Normalization techniques have become standard components of neural networks. Batch normalization normalizes activations across the examples in a mini-batch, stabilizing training and allowing higher learning rates. Layer normalization performs a similar role but normalizes across features within a single example, making it more suitable for sequence models. These normalization methods reduce internal covariate shift and improve optimization stability, though the precise mechanisms are still an active research topic. Neural networks are universal function approximators in the sense that, given enough parameters, they can approximate a wide range of continuous functions. However, this theoretical result does not guarantee efficient learning. In practice, the success of neural networks depends heavily on architecture design, optimization strategy, data quality, and computational resources. Much of modern AI progress comes from carefully engineering these components to work well together at scale. Different problem domains have driven the development of specialized neural network structures. In computer vision, convolutional neural networks exploit spatial locality by applying small filters that slide across the image. This dramatically reduces parameter count compared to fully connected layers and encodes translation invariance. In natural language processing, recurrent networks and later attention-based architectures were developed to handle sequential data where order matters. In graph-structured data, graph neural networks propagate information along edges between nodes. Another important idea is representation transfer. Neural networks trained on large datasets often learn features that are broadly useful. Instead of training from scratch, practitioners frequently start with a pre-trained network and fine-tune it on a new task. This approach reduces data requirements and training time. Transfer learning has been particularly transformative in vision and language domains. The scale of modern neural networks has grown dramatically. Early networks had thousands of parameters. Today's large models may have billions or even trillions. This scaling has been enabled by advances in hardware accelerators, distributed training infrastructure, and optimization techniques. Empirical evidence shows that performance often improves predictably with scale, though the computational and environmental costs are significant. Despite their success, neural networks have important limitations. They can be sensitive to small input perturbations, sometimes producing incorrect outputs with high confidence. They may encode biases present in the training data. Their internal representations are often difficult to interpret. They typically require large amounts of labeled data unless self-supervised techniques are used. Understanding and mitigating these limitations is an active area of research. From a systems perspective, deploying neural networks in real applications requires more than just training a model. One must build reliable data pipelines, monitor model performance over time, handle distribution shifts, and manage inference latency and memory constraints. Techniques such as quantization and pruning help reduce model size and improve efficiency. Knowledge distillation trains smaller models to mimic larger ones, enabling deployment on resource-constrained devices. Another conceptual lens for neural networks is energy-based modeling or probabilistic modeling. Some networks are trained to estimate probability distributions over data, while others directly learn decision boundaries. Generative models such as variational autoencoders and diffusion models learn to produce new samples resembling the training data. Discriminative models focus on predicting labels or values. Many modern systems combine both perspectives. Optimization landscapes in neural networks are highly non-convex, yet in practice gradient descent often finds solutions that generalize well. One hypothesis is that over-parameterized networks have many good minima connected by low-loss pathways. Another idea is that stochastic gradient noise biases optimization toward flatter regions of the loss surface, which correlate with better generalization. Although a full theoretical explanation remains incomplete, empirical practice has become highly effective. Neural networks can also be viewed through the framework of differentiable programming. In this view, the network is simply a large differentiable computation graph. This perspective allows integration of neural components with other differentiable modules such as physics simulators, memory systems, or routing mechanisms. The unifying requirement is that the overall system remains differentiable so gradients can flow end-to-end. As models grow more capable, questions of reliability, safety, and alignment become increasingly important. Neural networks optimize the objective they are given, which may not perfectly reflect human intent. Careful dataset curation, evaluation design, and post-training alignment methods are necessary to ensure desirable behavior in deployed systems. Looking ahead, research continues on making neural networks more data efficient, more interpretable, more robust, and more computationally efficient. Hybrid systems that combine neural learning with symbolic reasoning or external memory are being explored. Continual learning aims to allow networks to learn new tasks without forgetting previous ones. Neuromorphic hardware seeks to improve energy efficiency by drawing closer inspiration from biological computation. What remains constant is the core idea: artificial neural networks are flexible, differentiable function approximators trained with gradient-based optimization on large datasets. Their power comes from layered nonlinear transformations, large-scale computation, and the ability to learn representations automatically from data. Understanding these foundations provides the conceptual grounding needed to navigate the rapidly evolving landscape of modern AI.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.